Hey guys, so I found that a lot of schools and teachers require you to really just memorize um, random information often. And for myself personally, I really just can't learn through that style of teaching. And instead, I found that if I have a better understanding of the primary and core phenomenons that are happening and why they're happening, I can remember the material a lot better and simpler. So that's what I'm going to hopefully be doing today. Is I'll just be going through some of the more egregious, one of the most egregious examples that I have of this type of memorization that really hasn't worked well for me. Uh, where once I actually understood it, I was able to um, know it and truly understand it by heart, and then quickly explain that phenomenon to you in this with a deep and holistic understanding. Um, I said that weird, but it's fine. So to start off with, the problem that I will be looking at is um, we'll be talking about. Sorry, give me a second. Have a bit of a technical difficulty. There we go. So we'll be talking about osmosis. So osmosis is simply the separation of two different bits of water through with a semi-permeable membrane in between them, where one part of the water has a higher concentration and the other has a much lower concentration of water. Um, Sorry, not of concentration of water, concentration of salts or other particles. So in general, what you see is if you have a column or a membrane that has with a column or a cell or anything like that type with a semi-permeable membrane in it, or a selective membrane, as some people call it, then what you see is that you will have water flowing towards the more concentrated area. Um, and I've heard a lot of really weird and strange explanations as to why this is happening, so I decided to just make a bit of a video to explain what this phenomenon is and what is happening with it. So to start off, I'll just talk quickly about random molecular motion real quick. So in general, all molecules are moving entirely randomly. Um, the best explanation that I've really gotten towards this, towards making me really remember it and understanding it a lot better towards different phases and stuff, is like, if you think about it, a solid is pretty much like a group of people in a classroom. They're all sitting pretty much still in nice little organized rows and occasionally moving back and forth a little bit and wiggling. And a liquid is kind of like the exact same classroom of people if you gave them all highly crazy drugs and they were all out of their mind, running around the room at max speed, jumping on top of tables, running everywhere, and just a crazy absolute mess of people in a room. And then gases are like the exact same room, except for if you gave the students all jetpacks instead. So they, as you as the uh, craziness gets more and more, they take up more space, take up more area, and they tend to move a lot more at a lot faster pace. Um, Not sure if that helps you, but that's just the best quick explanation towards those phases that I've gotten that have really stuck with me. Uh, but I also just threw together a quick uh, demonstration of this sort of phenomenon, which is just a box. It will move in a random direction at a random direction every step, and will take hundreds of steps every second. And what you will see is that after as it continues taking these random steps, even though it's just purely moving randomly, um, it starts traveling farther and farther away from the origin point on average. And this will always be true for systems like this that are entirely moving randomly, is that given enough steps and given enough time, it will move significantly far away uh, from the origin point that it started from on average. However, as it tries to get farther and farther away, for every bit farther that it tries to go, it has to uh, it has to square how much time it takes to get that. For every additional bit of distance, it takes a squared amount more steps. Um, so I guess a better explanation of it is if you look at the steps taken over the distance traveled, then overall that will be equivalent to the squared amount of the step size. So for example, this time has a step size of about 10, so we expect the steps taken over distance traveled to be around 100 at any given time. However, as this is a random system and a live demonstration, it's not necessarily going to happen. However, at this time, we've seen that our box has traveled around twice as far as we expected it to have gone, um, which is an interesting uh, thing. But that is all for that example. And just to give you a bit of an idea of what that type of random molecular motion really is and what it looks like. It's also very important to note that molecular motion is very much based off of temperature, and that temperature it generally increases that molecular motion significantly. So then we'll go ahead and go on to our second topic. Apologies again, quick accidental. There we go. Sorry, I keep having issues with this client. But just to explain a different phenomenon, now that we've covered random molecular motion, I'll talk quickly about dissolving. So dissolving is the process of taking generally large solid objects and dissolving them into water. Uh, Often these are pills or powders. Um, I'm sure you've probably often done it with hot cocoa and plenty of other pills yourself. So this process is simply the breakdown of those materials into the water. And how that happens is that the water will just simply surround those molecules and become attached to them. This happens because the water molecules tend to have a positive and negative side, um, and those are attracted to the charged parts of the molecules. This causes those water molecules to be bound to the surface of it and have a lower overall thermal stability, which is probably a bit that is reaching too far for this specific video. So for now, I'll just leave it as that. However, you can actually determine how quickly something will dissolve inside of a fluid based off of the um, cross-sectional area of that is touching the fluid, multiplied by the diffusivity over the apparent thickness, which is a system constant based off of how quickly you're stirring your system and um, how like acidic it is, for example. And then that's multiplied by um, the equilibrium solubility, which is also known as the maximum solubility, or you might also just simply know it as the point that things stop dissolving, um, because the liquid is already saturated with that particular ionic compound or molecule. And then that's subtracted by the bulk concentration, which is the average concentration inside of that glass. You can very easily test this one out yourself with a bowl of water and some hot cocoa, as the hot cocoa will go onto the top layer of it and become a flat surface after you pour in the water, and then you can, if you know what that cross-sectional area of hot cocoa is, you can actually measure how quickly it dissolves, and you can directly measure the diffusivity of your water, and the diffusivity over apparent thickness of your water, by doing that, which is quite easily. There's also another one that you can, another way that you can do it with peeps, but a bit more gruesome on that one. Um, and then also in this dissolving phenomenon, as you can tell, it generally spreads throughout the entire glass, and slowly goes from one small corner of it and will slowly basically spread throughout the entire glass. This is based off of a different phenomenon, which is um, based through Fick's second law of diffusivity, um, which basically states that the rate of change of a concentration of particles is based off of the diffusivity or diffusion coefficient of the liquid, multiplied by the concentration gradient, which is just saying that the very simple explanation is saying that all molecules will tend to maximally spread out, but this Fick's second law is very much based off of what I mentioned at the beginning of random molecular motion, where because all of these molecules are moving randomly, they will spread out from that origin point very slowly over time and just keep spreading until they're eventually evenly spread out. However, if you're doing it into a large enough container, as mentioned, the time that it takes to go further and further away from the center is based off of the square of the distance. So as you get farther and farther away from that origin point of diffusivity, it becomes much harder to go farther away from the center and takes a much longer amount of time. So a more simple version of Fick's law that is a lot easier to look at is just that the flux is proportional to the diffusion concentration multiplied by the concentration gradient, and flux, real simply, is the transfer rate over the transfer area, or it's the amount of volume flowing through a area divided by the area. So it's a volumetric flow rate divided by the area that it's flowing through. So think liters per second divided by meters squared. And this is pretty simply done by just taking a moving, a cross-sectional area of your fluid, generally randomly, and then doing a balance across that box that you've drawn, and then balancing all of the mass in, energy, temperature, heat, momentum, and just doing a balance of all of those equations, as in generally any of those things that go into your box that you've drawn must come out of it. So if you do a balance over that, and you can for generally any system you can draw, if you can draw one box over it and perfectly describe that simple box, then you should be able to describe the entire system. For most systems, sometimes you can get very poor sample bias, however, but again, problems for another time. One very important part of both of these equations, however, is the diffusion coefficient, which is the rate of diffusion, or it's just generally considered a system constant, not, it, it's generally considered a system constant based off of the liquid that you're using and the temperature that you're using it at. And this is generally based off of the size of the particle. So if it's placed on the periodic table of elements, as well as the temperature. As I mentioned before, temperature has a lot to do with both volume as well as movement of the particles, and then it also has to do with the viscosity of the particles, which I haven't actually mentioned before, which is just the intermolecular forces that are above and beyond just pure random motion. As the pure random motion model gets a little bit complicated when it comes to other electronic attractions and forces that have those inherent attractions between it, as well as the momentum and movement that is expected. So then going into the last part of this section, quickly talking about filtration. So filtration is the flow of mass or water through a filter from one side out the other. It's generally one direction, single directional, and it generally takes a lot of time, effort, and filtrates based off of size. So anything that is large gets excluded. So this is important for this discussion, as the molecules, when surrounded, the salt ions and molecules, when surrounded by those water, that water is bound to it and will not generally break off or break free from those molecules, or at least will not break free very easily away from those molecules. So what this means is that those molecules, when surrounded by those cationic, ionic molecules that are dissolved into your water, when surrounded by the water molecules, become significantly larger in size than the water molecules themselves. So you can generally create membranes or barriers which allow water through them, but exclude those water-bound solutes. Quick explanation about what's happening through filtration. In general, the filtration rate, or the flux through the filter, is based off of the difference in pressure, or the pressure driving force, or the amount of pressure that it takes to push a bit of liquid through that filter. Sorry, no, the amount of pressure that you're applying to push that liquid through that filter, and then the broth viscosity, which is the viscosity of the fluid, again related to temperature and all of those things. And then lastly is the resistance to flow. The resistance to flow is the resistance caused by the filter itself, as well as the resistance caused by the particles that are building up on the filter. So as you filter fluid through this one directional flow, you are taking the particles out of the fluid and pushing them up against this filter. And after some time, you will see a visible cake building up on this filter, and that cake makes it significantly harder to push more liquid through the filter. So as you push more and more liquid through, more and more particles build up, and that cake becomes thicker and thicker. And there's the resistance of the cake is based off of just variables based off of entirely what you're filtrating out, as well as how quickly you're filtering it and how much pressure you're using. And it's generally so variable that it's hard to exactly describe for uh, one given system. However, for this explanation, as long as you know that the resistance is caused not only by the filter but also by the particles, it should be plenty of an understanding. Um, so going back to osmosis and tying everything together a little bit, so that semi-permeable membrane that we have at the center is really just a filter that's stopping all of those bound water molecules from going through, but it's allowing the water to go through. So what's happening that's causing this osmotic pressure to be forming, and that difference in height in between the two columns to form, is that the salt molecules are actually clogging up the filter when trying to go back. However, when the water is going the one direction, it's just free flowing because it doesn't have nearly as much salt particles blocking the filter, because the salt particles only block the membrane in one direction, which is an important piece to know about this system. And that's what causes that pressure difference at the top and that height difference. So if we break down the actual math a little bit, then we can look at the actual statements of what's happening, and we see that the volumetric flow-through rate, this is standard. Simply, if we say that the system is at equilibrium, so there's no volumetric flow-through rate whatsoever, and then we set them equal to each other, then we find that the pressure driving force over fluid velocity, viscosity multiplied by that resistance particle part is equal to each other, and we set those two equal to each other as mentioned. Then we can simplify the equation a little bit, and we can see that the difference in that height, or the difference in pressures, which is directly related to a difference in height, as pressure at the membrane is based off of the height of the fluid column multiplied by the density of the liquid. So the difference in pressures, or the difference in heights that you see, is directly related to the pressure on the one side multiplied by the concentration in the other side divided by the concentration is directly related to the resistance in the other side divided by the resistance in the of the membrane subtracted by the other one. This is a little bit difficult to this bottom equation is a little bit difficult to understand by itself. So if you set one of the two concentrations to 0, just to simplify it out. So for this one, I'll say that the left-hand side of this equation has 0 concentration of solvent in it, and the right-hand side has an unknown concentration of solvent in it. So if we do that, then we see that this whole second part cancels out of the P2, and we see that the difference in pressures is equal to the pressure on the left-hand side of the column multiplied by the ratio in between the resistance caused by the particles and the resistance of the filter. Which, again, I'm not 100% sure if this is super helpful. However, it does strongly suggest that this osmotic pressure that builds up is strongly dependent on the resistance of the membrane itself that is separating it as well. So if you have a thicker membrane, then uh, then it'll have a lower osmotic pressure, and if you have a thinner membrane, then it'll have a higher osmotic pressure. I'm not 100% sure as to how accurate that is, and I'd have to test it myself. However, this equation does overall make sense. There is a bit of a simplification that I did make when creating this equation, however, which is that this equation is a equation for that was created assuming singular flow of motion, uh, and also created assuming that the particles would allow partial flow through even when blocking up the filter, which is likely incorrect, and it's probably much more accurate to say that the particles are causing complete blockage when they block flow through from one side, um, which is a different set of equations that is um, a bit more complicated, and I'm not too sure as to the setup for that system of equations. Um, so thank you very much for your time. This has been interesting. Uh, hopefully I can continue this some other time with a different um, type of equation and a different, yeah, I'll just end it there. But again, thank you so much for watching.